This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the scoring guidelines for the 2019 AP Calculus exam, free response question BC2. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading in Kansas City. I'll present a brief general summary for student performance on this question, and then I'll consider more detailed interpretations of the scoring guidelines and how these guidelines were applied in certain situations. I'll consider some common student errors where it's relevant, and where appropriate, I'll present some specific scoring examples. This free response question involves a polar curve, r of theta equals 3 times the square root of theta times the sine of theta squared, for theta between 0 and the square root of pi. The graph of this polar curve is shown in this figure, and S is the region bounded by or enclosed by this curve. In Part A, we need to find the area of the region S. In Part B, we need to find the average distance from the origin to a point on the polar curve for theta between 0 and the square root of pi. In Part C, we're told that there is a line through the origin with slope m that divides the region S into two regions of equal area. And we need to write an equation whose solution yields the value of m. And finally, in Part D, A of k is defined to be the area of the portion of S that lies inside the circle r equal k cosine of theta. And we need to find the limit as k goes to infinity of A of k. Part A was worth 2 points. 1 point for writing the integral that leads to the area, and 1 point for the correct answer. Part B was also worth 2 points. Similarly, 1 point for writing the integral that leads to the average distance, and 1 point for the answer. Part C was worth 3 points. The first point was for writing an expression that equates two polar areas. The second point was for using an inverse trig function applied to m as one of the limits of integration. And the third point was for the final equation. Part D was worth 2 points. The first point was for the correct limits of integration, and the second point was for the correct answer attached to or associated with a definite integral with limits that earned the first point. Here are some general comments about student performance on this question. In Part A, most students were able to set up the definite integral for area. That is, most knew to use r of theta squared as the integrand and to include the constant 1/2. However, there were some presentation errors, and most of these involved parentheses errors, in which the student elected to write out the expression for r of theta. In Part B, some students used the formula for arc length. I'm not really sure why. Some students used the expressions that relate rectangular coordinates to polar coordinates, and they constructed a formula for distance and integrated successfully. This was, I think, a longer way to get to the answer, but mathematically correct. A common error involved this expression with the square root of pi. I guess this is sort of an average area, but it's incorrect. And there were some presentation errors here also, most notably sine squared of theta versus the sine of theta squared. In Part C, some students had trouble connecting the slope of the line to a polar equation. And a common error here was the use of r of theta instead of r of theta squared. And some students used m or even the tangent of theta as a bound on a definite integral. In Part D, written justification was not required to use the bounds 0 and pi over 2. However, some students had trouble connecting the concept of limit to area and to arrive at these bounds. And some students did not present a definite integral or simply tried to use the result for area from Part A. Here are just a few general notes about scoring this problem before we take a look at the rubric a little closer. There are 2 points in this question in Parts A and B specifically for the integral, and this means the limits as well as the integrand. The constant in front, or the coefficient on the integral, is not part of the integral or the integral point. Remember, this was a calculator active question, so unfortunately some students had their calculator set in degree mode, and we had a very fair way to recognize this error and award points appropriately. The given function contains a square, and unfortunately there were some errors that involved a square. These two functions are not the same, and this was a common error. There were several presentation errors in this problem. However, a student could be inoculated from further similar presentation errors after committing the first error. And there was a general philosophy in scoring this problem. The student needed to communicate an understanding of how polar area is determined. They must be aware of the parts of the polar integral. Specifically, the bounds on the integral must be angles. And then they must be able to apply and connect several concepts. The first point in Part A was for the integral. And remember, this includes the bounds on this definite integral. And we must see one of these two integrals for the student to earn the point. Now, the student can certainly use r of theta since it was defined in the problem, and I would advise them to use this function name. There is more chance of a copy error if the student attempts to write the expression for r of theta. The coefficient 1/2 is not part of the first point. A missing d theta is not penalized as long as the integrand is clear. In other words, a missing d theta could make the integrand ambiguous, in which case the student would not earn this point. And finally, this integral, in which the integrand is not squared, does not earn the first point. The second point in Part A was for the answer. A bald answer was not accepted here. There has to be supporting work. And to earn this point, the student must present our answer only, 3.534. Now that sounds kind of funny, but we're not reading for or checking answers here that correspond to incorrect integrals. Now the student may of course present an exact symbolic answer. This was a calculator active question, and a CAS calculator might return this value. And if the 1/2 is missing, the student does not earn this second point. Here are some example student responses in Part A and how each was scored. In Example 1, the student has the correct integral, the 1/2 is present, and they had the correct answer. They earned both points in Part A. In Example 2, the student does not have the correct integral, the square is missing, and they do not have the correct answer. This earns 0, 0. In Example 3, the student does not have the correct integrand. They do not earn the first point. But the bounds are correct, the 1/2 is present, and 3.534 is the correct answer. This is treated as a presentation error. The student does not earn the first point, but earns the second. The first point in Part B was for the integral. And we need to see one of these two expressions, including the bounds. The coefficient, or the constant in front of the integral, is not part of this point. Now some students attempted to find arc length in this part and presented one of these two expressions. This work does not earn any points in Part B. And some students used the distance formula from a point xy to the origin. This was a little longer, but it was a valid mathematical approach, and a student could earn both points here. The second point in Part B was for the answer, And again, a bald answer did not earn any points in Part B. And the answer must be one of these three values. If the student omits the constant 1 over the square root of pi, then they did not earn this second point. Here are some example student responses in Part B and how each was scored. In example 1, the student has presented the correct integral, the constant is correct, and the answer is correct. This earns both points in Part B. In example 2, the integrand is wrong. There's an extra square. But the bounds and coefficient are correct, and the student has produced the correct answer. So we'll interpret this similar to an example in Part A. This is a presentation error. The student does not earn the first point, but earns the second. In example 3, the integral is incorrect. Note that in addition to the incorrect integral, there are no bounds presented. There's an extra 1/2 and the answer is wrong. Yikes! This earns 0, 0. In example 4, the distance formula is used with the expressions for x and y in terms of r and theta. Everything is correct here. This earns 1, 1. In example 5, the student is also using the distance formula, but has to tell us how x and y are defined. And this is not a general formula because r is defined in the problem. So this also earns 1, 1. Part C was worth 3 points. The first point was for equating polar areas. Now, this means we must see a structurally correct equation involving at least one polar area integral. And structurally correct means the student has conveyed a polar integral equal to 1/2 the area found in Part A. If there is a presentation error in one integral, but the equation is still structurally correct, the student earns the first point but cannot earn the third point. Some common presentation errors included a parentheses error, the lack of a square, or the misrepresentation of r theta. This would be interpreted as r times theta. There were several common acceptable equation forms, and here are some of them. In each case, we believe that the student understands the concept of polar area and has made a connection to our problem. The or equivalent in forms 2 and 3 means that the student could use bounds of some angle greater than 0 up to the square root of pi. Here are some example student responses focusing on the first point only in Part C and how each was scored. In example 1, there is at least one polar area integral. The bounds are wrong, but this is still structurally correct. This earns the first point. In example 2, there is at least one polar area integral. Well, there are two here. The bounds on the left integral are wrong, but again, the equation is structurally correct and earns the first point. In example 3, even though there is no constant 1/2, this is a structurally correct equation, so this earns the first point. In example 4, even though there is at least one polar area integral, the equation is not conceptually correct. Now this is subtle. Note the difference between this example and example 3. This does not earn the first point. And in example 5, this equation is not a correct interpretation of the problem. In fact, this equation has infinitely many solutions. So this does not earn the first point. The second point in Part B was for using an inverse trig function applied to m as a limit of integration. To earn this point, there must be an integral with limits that are two angles, and one limit must involve an inverse trig function that somehow incorporates m. Now this point can be earned even if the integral does not represent area, and here are two examples. And here are some examples of acceptable limits and a few that are unacceptable. The third point in Part C was for putting the first two conceptual ideas together and for presenting a correct equation. And there was an eligibility criteria here. The student must have earned the first 2 points. And they must have one of our acceptable forms from the first point with correct limits. Here are a few examples of student responses and how each was scored. In example 1, the student has equated polar areas. The equation is structurally correct, and as long as the expression m equals a tangent of theta is present, the equation is correct. So this earns all 3 points in Part C. In example 2, the student has equated polar areas. The equation is conceptually correct with the use of an inverse trig function as a bound, but the equation is not correct because the inverse trig limit is wrong. This earns 1, 1, 0. Example 3 was actually a common student response. Here, the student defines the value q, but not appropriately. So there is at least one polar area integral. There is no evidence of an inverse trig function, and therefore they are not eligible for the third point. So this earns 1, 0, 0. In example 4, if m represented an angle, this equation has infinitely many solutions. So the student has not equated polar areas, there is no use of an inverse trig function, so they're not eligible for the third point. This earns 0, 0, 0. Part D was worth 2 points. The first point was for using the correct limits of integration, 0 and pi over 2. Now, it was okay to use 1.571 for this point, but using this approximation does not yield the correct final answer. However, this does demonstrate a conceptual understanding of the limit process. That is, as k increases without bound, then the circle r equal k cosine theta will eventually contain the portion of the region S in quadrant 1. The second point in Part D was for the answer with a supporting integral, and there was an eligibility criteria here also. The student must have earned the first point. So 0, 1 is not a possible score in Part D. Now the answer must be our answer, 3.324. If the student uses 1.571 as a bound on the definite integral, but reports the correct answer, then they earn 1, 1. And here's one lonely example of a student response in Part D. Here the student has the correct bounds on the definite integral, indicating an understanding of the limit process. They earn the first point, and they are eligible for the second. But the integrand is wrong, and the answer is, therefore, wrong also. This earns 1, 0. At the AP Calculus reading, an actual briefing for the scoring of a free response question usually takes approximately 75 minutes. And there is also time allotted in the reading rooms for discussion before the actual scoring begins. However, I hope this summary video gives you a good idea of how this question was scored. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.